Everyone talks about the cool stuff, the AI, the predictive models.
Hmm.
But honestly, the real work, the secret struggle in data science, it's fighting the chaos in the data itself. There's this widely accepted stat, it's pretty staggering, that something like 80%.
Yeah.
80% of the time on a data project is just spent preparing the data, cleaning it, transforming it, wrestling it into shape, data munging, as they sometimes call it.
Exactly. It's the messy bit.
So if you're looking for a clear map through that, that massive necessary workload, well, this deep dive should give you that shortcut.
It really is the crucial step between just raw, jumbled information and something you can actually use, something that gives accurate insights. And data cleaning, it's not like you do it once and you're done. It's iterative. You keep finding things, fixing things before you can even think about analysis or modeling.
Right, and if it's directly in the standard process flow, if you're familiar with CRISP-BM, we're talking phase 3 here, data preparation. You've looked at your data, maybe understood it a bit. Now you have to make it, well, usable.
Precisely. Raw data. It's almost never fit for purpose right out of the box, whether it's from a database, scraped off the web, whatever. It's got flaws. And if you don't put the time in here, seriously dedicate the effort, then whatever fancy model you build later, it's basically built on quicksand. It's that classic garbage in, garbage out problem.
Yeah, G.I. Joe.
And our mission today really is to show you how to stop that garbage getting in.
Okay, so let's dig in. If we're spending potentially 80% of our time on this,
Yeah.
how do we actually know when the data is clean? When are we done? We need some kind of benchmark, right? A definition of quality.
We do, yeah. There are key dimensions we look at, and they're often summed up with this handy acronym, ACUCVT. Think of it as like a health check for your data.
ACUCVT.
Okay. So first up, A is for accuracy. Simple enough. Is the data actually correct? Does it reflect reality? If it says a customer lives on Mars, probably not accurate.
Probably not.
Then C is for completeness. Do we actually have enough data? If, say, 90% of a really critical column is just empty, well, it's not complete enough for what you need.
Makes sense. And you mentioned duplicates earlier.
Right. That's the U for uniqueness.
Yeah.
Are there identical or essentially identical records floating around? And then the second C, that's consistency. This is where you get tripped up by formatting differences.
Oh, yeah. Like state names.
Exactly. Is it California, CA, or maybe KLF? Those kinds of inconsistencies, they have to be ironed out. Then V is for validity. Does the data follow the rules it's supposed to? Like an age field should probably only have positive whole numbers, right?
Right.
And finally, T is timeliness. Is the data still relevant? You might have perfectly accurate customer data from 1998. It's probably not timely for predicting buying habits today.
Okay, ACUCVT, that gives us clear targets. So practically, where does someone start? Is it always about profiling the data first, just figuring out where it fails on those ACUCVT checks?
Absolutely. Profiling is step one. You need to see the current state of, well, the chaos. But, the better goal, long term, is to stop the chaos before it starts.
Proactive, yeah.
Yeah. Setting up strict checks before bad data even gets saved. And doing regular quality reviews because data sources change, systems drift, new problems pop up. It's dynamic.
Let's zoom in on maybe the most common headaches, missing values, and those duplicates you mentioned. Duplicates seem easy, right? Just delete the extra row. But isn't there sometimes a gray area? Like, what if two different people just happen to have the exact same values for, 50 different fields?
That's a fair point. It can be ambiguous, but usually, if you're pretty sure they represent the same actual thing or person, the simplest, safest bet is just deletion of duplicates. Tools like Pandas make it super easy, like with a drop duplicates command. You basically assume it's redundancy and remove the ambiguity.
Okay, simple enough for duplicates usually.
Okay.
But the real beast seems to be missing values, because so many algorithms, especially older ones, just fall over when they hit a null or a nan.
They really do.
Huh.
And to handle missing data well, you first have to think about why it's missing. There are these different mechanisms, what we call missing data models, 3 main types. The simplest scenario is MCAR, missing completely at random. Basically, the chance of a data point being missing is totally random. It has nothing to do with any other data you have. Think someone just randomly skipped a question on a survey.
Right.
If you have MCAR data and it's a very small amount, like maybe less than 2% of your data set, you can often just delete those rows without introducing much bias.
Okay, that's the easy one. What's next?
Then you have MNAR, which is missing at random. Now, this sounds similar, but it's trickier.
How so?
With MNAR, the missingness is predictable, but only if you look at other information you do have. So imagine you're collecting salary data. Maybe only the high-level executives tend to skip that question.
Oh,
So
cool.
whether the salary is missing depends on their job title, which you do know. But within that group of executives, who skips it might still be random MNAR data.
Well, we can often model that relationship and impute the missing values reasonably well.
Okay, so related to other observed data, what's the really difficult one then? That's MNAR, missing not at random. Here, the reason it's missing is related to something you don't know, something you haven't measured. Maybe people with really, really low credit scores just don't bother applying for a loan in the first place. You don't see the low score or the application.
Ooh, that's tough.
Yeah, it's often systemic, hidden. Fixing MNAR often requires going outside your current data set, doing more investigation. It's the hardest to deal with properly.
So deleting often isn't an option, especially with MR or MNAR, or just too much missing data. That leaves us to imputation, right?
Right.
Filling in the gaps. The simplest ways we see are using the mean, median, or mode. What's the catch there?
The big catch is, well, you're creating artificial data that looks maybe too perfect. If you fill 10% of missing values with the exact same mean, you've just squashed the variability in that part of your data.
That you lose the real spread.
Exactly. Your data looks tighter, cleaner than it really is, and that can fool your model later. It might become overconfident, or it might underestimate how much things actually vary in the real world.
So, fast and easy, but you pay a price in fidelity. How do we do better? Get more sophisticated with the imputation.
Well, we can move beyond just one static number. You can use methods like forward fill taking the last known value, or backward fill taking the next known value. Or you can get even smarter and use model-based imputation, like k-nearest neighbors regression.
How does that work?
It finds other records in your data that are most similar to the one with the missing value based on all the other columns you do have. Then it uses the values from those neighbors to estimate or impute the missing one.
That sounds much more tailored.
It is. And we should also mention, there's a bit of a get-out-of-jail-free card sometimes. If your missing data is really quite minimal, maybe 5% or less, and you happen to be using certain modern algorithms, especially tree-based ones like XGBoost or like KeyBM,
Yeah, those are popular.
they can actually handle missing values internally. They have built-in ways to deal with NANs during training, often by sending them down a specific path in the tree. So sometimes you can just leave them be. Saves effort, but only if the missingness isn't too widespread.
Good to know. Okay, so we've tackled missing data. Let's shift from those statistical fixes to more real-based cleaning. This feels like it connects back to that validity part of ACUCVT, right? Making sure data follows real-world logic using integrity constraints.
Exactly. Integrity constraints are basically mandatory rules the data has to follow. The most common are things like range constraints. A percentage column has to be between 0 and 100.
Simple enough.
Or uniqueness constraints, like a customer ID must be unique. And super important in databases is referential integrity. Basically, if one record points to another record, like using a foreign key.
Like an order points to a customer ID.
Precisely. That customer ID it points to must actually exist in the customer table. The link has to be valid.
And then things get interesting when you have rules that span multiple fields, right? Like catching logical errors. You shouldn't have someone discharged from the hospital before they were admitted.
Exactly. Those cross-field validations are key. But let's push the complexity a bit. What if the issue isn't that a value breaks a rule, but that you're not even sure who or what the record is about? This gets us into entity resolution.
Right. The classic problem. Is J. Smith the same person as John A. Smith? And maybe J. Alexander Smith at a different address? Deduplication, record matching, figuring that out.
Yeah. And once you've hopefully figured out who the entities are, you might face another problem, truth discovery. This crops up when you pull data from multiple sources and they disagree.
Like, source A says the customer lives in Boston. Source B says Cambridge. Which one do you believe?
Exactly. Now, the naive approach is just majority voting. If two sources say Boston and one says Cambridge, you go with Boston.
Seems reasonable.
But what if that one source saying Cambridge is your gold standard, recently updated CRM, and the other two are old, unreliable lists? Majority vote gives them equal weight, which is wrong.
Right. Not all sources are created equal.
That's the core issue. More advanced methods, like the approach used in algorithms like TruthFinder, change the game entirely. Think of it like judging witnesses in court. You don't just count votes, you assess the credibility of each witness first.
How does TruthFinder do that?
It works iteratively. It estimates two things simultaneously. how truthful each source generally is, based on how often its claims agree with what other good sources say, and how confident we should be in each specific value.
So it learns which sources to trust over time.
Essentially, yes. If a source is consistently accurate across many data points, its vote on the tricky Boston-Cambridge question carries more weight. Sources that often provide conflicting or wrong info get downweighted. It leads to a much more reliable answer than simple voting.
That's a much smarter way to handle conflicting info. Okay, before we leave the cleaning part, we have to talk about outliers. But let's be clear on the terms. An error breaks a rule, like December 32nd. An outlier is different, right?
Totally different. An outlier doesn't necessarily break any hard rule. It's just way out there.
Yeah.
Anomalously far from the bulk of the data, like maybe a CEO's salary in a data set of mostly entry-level salaries. It might be correct, just extreme.
So how do we spot these, especially the numerical ones?
For single variables univariate outliers, a really common and robust method uses quartiles. We calculate the IQR, the interquartile range.
That's the distance between the 75th percentile and the 25th percentile, right?
Yeah.
The middle 50% of the data?
Exactly. Then we use the famous 1.5 times IQR rule. We calculate an upper fence, which is the 75th percentile plus 1.5 times the IQR, and a lower fence, the 25th percentile, minus 1.5 times the IQR. Anything falling outside those fences. We flag it as a potential outlier.
And that 1.5 multiplier, that's just a standard convention. It lines up with the whiskers on a box plot, visually.
It does. It's a pretty standard way to define what's reasonable variation versus suspiciously far out. But sometimes an outlier isn't obvious looking at just one variable at a time.
You mean multivariate outliers?
Right. A data point might look perfectly normal on its height value and perfectly normal on its weight value, but when you look at height and weight together, it's weirdly out of step with everyone else.
How do you catch those?
There are more advanced techniques. One popular one is isolation forest. The idea is kind of neat. Imagine your data points are houses in a city. Outliers are like isolated cabins way out in the woods.
Okay.
Isolation forest works by randomly cutting the data space. It takes very few random cuts to isolate one of those remote cabins, but it takes many, many cuts to separate two houses that are close together deep inside the city. So points that get isolated quickly are likely outliers. It's very efficient.
Clever. Okay, outliers identified, maybe dealt with. Now, the last big prep step for numerical data, scaling. Why do we absolutely need this for some types of algorithms?
Right, think about it like this. Imagine you're measuring two features for, say, customer similarity. One feature is age, ranging maybe from 20 to 80. The other is annual income, ranging from, I don't know, $30,000 to $1 million.
Huge difference in scale.
Exactly. Now, if you use an algorithm that relies on calculating distances between points like k-means clustering or k-nearest neighbors,
The income variable, with its massive range, is going to completely dominate that distance calculation. The age variable will barely even register.
precisely. The algorithm effectively ignores the smaller scale feature. Scaling fixes this. It puts all your variables onto a similar scale so they contribute more equally to the distance math.
Makes sense. What are the main ways to do that?
Two main workhorses here. First is min-max normalization. This squishes or stretches your data so it fits neatly into a specific range, usually 0 to 1.
Okay, simple mapping.
Simple mapping. It's good because it's easy to understand, and it works well if your data doesn't really follow a nice bell curve if it's not Gaussian. But, big warning, min-max is very sensitive to outliers. Because the outlier sets the absolute min or max.
You got it. One extreme value can totally warp the scaling for all the other points.
Okay, so if you have outliers, min-max might be risky. What's the alternative?
The main alternative is standardization, also called z-score scaling. This transforms the data so that it has a mean of 0 and a standard deviation of 1.
So it centers the data and makes the spread consistent.
Exactly, because it uses the mean and standard deviation, which are less sensitive to extreme outliers than min and max are. Standardization is often preferred when you do have outliers, or when your data roughly follows a bell curve, a Gaussian distribution. It keeps the shape of the distribution but removes the scale difference. Okay, that covers the numbers. Cleaned, outliers handled, scaled. Final big hurdle, text data. Machines don't speak English or any human language natively. So we need categorical encoding.
Right. Algorithms need numbers. So we have to translate those text labels like red, green, blue, or high, medium, low into some numerical format. The absolute most common way is one-hot encoding, or sometimes called dummy encoding.
How does that work again?
For every unique category value, red, green, blue, you create a brand new column. That column is binary. It gets a 1 if the original record had that category and 0 otherwise. So red might become a column vector, 1, 0, 0, 0, green, 0, 1, 0, etc.
Okay, clear representation, no implied order.
Exactly. It's safe because it doesn't accidentally tell the algorithm that blue is somehow greater than red, but it comes with a potentially huge downside, especially if you have lots of categories.
Like hundreds of unique city names.
Precisely. If you have a column with 500 unique categories, one hot encoding instantly adds 500 new columns to your dataset. This is the curse of dimensionality.
Sounds ominous.
It can be. You end up with tons of columns, most of which are zeros for any given row that's sparse data.
Yeah.
In very high dimensions, distance calculations like Euclidean distance start to lose their meaning. Models can become much slower, harder to train, and might overfit.
So if one hot blows up our data set, what are the smarter alternatives?
Well, one simple one is label encoding. You just assign an integer to each category, 1 for red, 2 for green, 3 for blue. It's compact, just one column.
But wait, didn't we just say we don't want to imply an order?
Exactly. That's the danger. If your categories are truly nominal, no natural order, label encoding is risky because many algorithms will interpret 3 as being more than 1. Fine for ordinal data like low, medium, high, but bad for nominal like city names.
Okay, so label encoding, use with caution. What else?
Another clever one is frequency encoding. Instead of the label itself, you replace the category with how often it appears in the dataset. So if red makes up 40% of the data, you replace red with 0.4.
Interesting. Why is that useful?
It naturally groups rare categories together because they'll all have low frequency values. It can sometimes capture useful information about how common a category is, and it controls dimensionality.
Okay. And is there one that tries to capture predictive power directly?
Yes, and that's often the most powerful, but also the trickiest. Target encoding, sometimes called mean encoding. Here, you replace the category label with the average value of the target variable for that category.
Whoa, okay. Give me an example.
Let's say you're predicting customer churn, yes, no, or 10, and you find that for customers in the category region A, the average churn rate is 90%. With target encoding, you'd replace region A with the number 0.9.
So you're directly injecting information about the relationship between the category and what you're trying to predict.
Exactly. It can give a big performance boost, but you have to be very careful doing it to avoid data leakage, where information from the target accidentally leaks into your features, making your model look good in training, but fail in reality. You usually need careful cross-validation techniques to implement it safely.
Wow, okay. We started this talking about the 80% problem, how much time goes into just TREP, and we've covered a lot of ground. We mapped out defining quality with ACUCVT, then diving into managing missing data, understanding MBR, MR,
MNAR.
right, and the imputation strategies. Then ensuring validity with rules, dealing with tricky things like entity resolution and truth discovery using methods like Truth Finder, and finally, tackling outliers with the IQR rule or isolation forest, and then getting the data ready for models through scaling and all those different encoding techniques.
It's quite the journey.
It really is.
Yeah.
Hopefully you listening now have a much clearer structure in mind and some specific tools like that 1.5 IQR rule, or knowing when not to use label encoding, or the risks of the curse of dimensionality to tackle your next data prep challenge more confidently.
Absolutely. And maybe just one final thought to leave you with, connecting back to the bigger picture. All this transformation, all this cleaning, it's crucial. But we also need to think about the risk of inadequate transformations, or maybe overly specific transformations.
What do you mean?
Well, what happens if you meticulously clean and scale and encode your data perfectly for one specific analysis for application A, but then next month, application B needs that same data, but maybe it needs the original distribution or a different type of scaling if you've transformed it too irreversibly for just one purpose.
You might have to undo it all, or worse, go back to the messy source.
Exactly. So the ultimate goal isn't just clean data for this model right now. It's aiming for clean, well-understood, and flexible data that can support multiple uses downstream without needing a complete overhaul every single time. It's as much a data governance challenge, really, as it is a technical one, something to keep in mind.